Every clock ever built is a confession of ignorance. Not ignorance about how to measure time, humanity mastered that centuries ago, and today we do it with a precision that borders on the surreal, carving reality into slivers so thin they make a billionth of a second look bloated and crude. The confession runs deeper than that. Every clock, every ticking mechanism, every atomic oscillator humming in a cold laboratory confesses the same stubborn truth: we still do not know what it is counting. We measure time with breathtaking accuracy. We understand time almost not at all. This is not a minor gap waiting to be closed by a diligent graduate student. It is a canyon running through the center of modern physics, separating our most successful theories from one another, separating the mathematics from the experience, separating the tick of the clock from the nature of the thing being ticked. Three of the greatest theoretical frameworks ever devised by human minds, classical mechanics, relativity, and quantum theory, each carry within them a completely different portrait of time. And when you place those portraits side by side and look at them carefully, they do not show the same subject. They seem to depict three different universes. Understanding why that gap exists and why it has resisted every attempt to close it for over a century is one of the most dramatic stories in the history of human knowledge. It begins with certainty, with a philosopher-mathematician who thought the matter was settled. And it spirals outward into territory so strange that physicists today argue, with complete seriousness and rigorous mathematics, about whether time exists at all. Start with the feeling. You know it right now, sitting wherever you are, reading these words. Something is moving. Something is passing. There is a before and an after, and you are sliding from one to the other without being asked, without stopping, at a pace you cannot alter. Your heartbeat marks it. Your breathing marks it. The slight fatigue behind your eyes marks it. Time is perhaps the most intimate feature of being alive, closer than breath, more persistent than thought. It is so woven into the fabric of experience that imagining its absence is nearly impossible. What would it even mean for time not to exist? The question seems absurd, almost offensive. And yet that question, along with the slightly less radical but equally vertiginous question of what time actually is, has driven some of the most brilliant scientific minds in history to the edge of understanding, and sometimes right over it into bewilderment. If you want to understand why, you have to start not with the frontier, but with the foundation. You have to start in the 17th century, in the mind of a man who thought he had solved it. Isaac Newton published his Principia Mathematica in 1687, and it is difficult to overstate what that document accomplished. It did not merely explain how objects move. It invented, in a form still recognizable today, the very concept of a physical law, a precise mathematical statement that nature is obliged to obey, everywhere, always, without exception. The laws of motion Newton laid out in those pages explain the fall of apples and the orbit of the moon with the same equations. They predicted where a cannonball would land, how tides would rise and fall, why the planets trace ellipses rather than circles. For 2 centuries after Newton, physics was essentially a project of filling in the details of his vision. But before Newton could write any of his laws, he had to make a decision about the stage on which all physical events take place. He had to decide what space and time were, and he made that decision in language so confident, so serene in its certainty, that it reads almost like a decree. Near the beginning of the Principia, Newton described what he called absolute time, not the time we read off clocks and sundials, which he acknowledged as approximate and practical, but the real thing underneath. He wrote that this absolute time flows equably, of its own nature, without relation to anything external. It ticks forward at a uniform rate everywhere in the cosmos simultaneously. It was before the universe and will be after it. It is not a thing inside reality. It is the frame of reality itself, the invisible metronome to which everything dances. This was not a wild or desperate guess. For Newton, it was the only picture that made sense. If you were going to write equations that describe how objects move, equations that contain a time variable and use it to calculate positions and velocities, you need that time variable to mean the same thing everywhere, and to all observers. You need a universal now. You need a shared timeline. You need to be able to say, without qualification, that at this moment, the same second is elapsing for you and for a sailor rounding Cape Horn and for a falcon diving in the Alps. Without that universality, the elegant machinery of Newton's laws would have no floor to stand on. If you find that picture intuitively compelling, you are in extremely good company. For over 200 years, every working physicist accepted it without serious question. Newtonian absolute time was not a hypothesis under scrutiny. It was a background assumption so fundamental, so embedded in the practice of physics, that questioning it would have felt roughly as productive as questioning whether numbers were real. The predictions worked. The equations were tested against observations, against pendulums and planets and projectiles, and they matched. What more could anyone ask? But there were hairline cracks, invisible without close examination. Two of them are worth studying, because they hint at what was coming. The first crack has to do with direction. Newton's laws of motion are time-symmetric. Run any process they describe forward, and the physics is valid. Run it backward, and the physics is equally valid. Film a pair of billiard balls colliding on a frictionless table and play the film in reverse. The reversed collision obeys every one of Newton's laws just as perfectly as the original. The mathematics does not know which direction time is pointing. It works equally well in both. And this is not just Newton's mechanics. Maxwell's equations of electromagnetism are time-symmetric. Einstein's field equations of general relativity are time-symmetric. Even the core equation of quantum mechanics, the Schrödinger equation, evolves states in a way that is symmetric under time reversal in the appropriate technical sense. The laws of physics, taken together, are almost completely blind to the difference between past and future. They work the same way, regardless of which direction the clock is running. And yet the universe is overwhelmingly, stubbornly, irreversibly directional. You have never watched a shattered teacup spontaneously reassemble itself. You have never seen a cold cup of coffee extract heat from the air around it and grow hot. You have never observed a puff of smoke gather itself back into the cigarette from which it came. The universe evolves in one direction, from order toward disorder, from concentrated energy toward diffuse energy, from structured arrangements toward chaotic ones, and never in reverse. There is an arrow of time so obvious, so universal in our experience, that it seems to require no explanation. But given that the fundamental laws are time-symmetric, it demands a very deep one. The answer, as physicists eventually worked out, lives in thermodynamics, in the concept of entropy. Entropy is a measure of how many microscopic arrangements of a system could produce the same macroscopic appearance. A freshly poured glass of dye sitting in clear water has low entropy. The molecules are all concentrated in one region. An hour later, when the dye has spread through the water uniformly, the entropy is high. The molecules could be arranged in an astronomical number of different ways and still produce the same uniform color. The second law of thermodynamics says entropy tends to increase, not because any law pushes it, but because there are so many more high entropy states than low entropy ones that random evolution almost always moves toward them. It is statistics, not law. There is nothing forbidding the dye molecules from gathering back into a concentrated region. It is just so wildly improbable that it will never happen in practice. This thermodynamic arrow of time is real and powerful. It explains why heat flows from hot to cold, why perfume diffuses through a room, why aging moves in one direction. But notice the deep strangeness hiding inside the explanation. The arrow of time that we experience, the arrow that makes the past feel irrecoverably gone and the future genuinely open, is not built into the fundamental laws. It is a consequence of initial conditions. The early universe happened to be in a state of extraordinarily low entropy. As time progressed, entropy increased because there were so many more places to go. If the universe had started in a high entropy state, there would be no arrow. Past and future would be equally disordered, equally directionless. The arrow points the way it does because of how the universe began, not because of any asymmetry in the laws themselves. Why the universe began in a state of such low entropy is not understood. It is called the past hypothesis, a brute fact about initial conditions that physics can describe but cannot yet explain. And that means the most basic feature of our experience of time, the fact that it seems to flow in a direction, the fact that the past is fixed and the future is open, is not fundamental. It is emergent. It is statistical. It depends on something we don't fully understand about the birth of the universe. That is the first crack. The second crack is subtler. It was articulated most powerfully, not by Newton, but by his contemporary and intellectual rival, the German philosopher and mathematician Gottfried Wilhelm Leibniz. Leibniz rejected Newton's absolute time with a philosophical argument of great elegance. He pointed out that we never experience time directly. We experience change. We see the hands of the clock move. We watch the sun cross the sky. We feel the fatigue accumulating in our muscles. From these changes, we infer the passage of time. But if all change were to stop, every atom frozen, every photon halted, every process in the universe suspended, we would have no way of knowing whether time was still passing. There would be no measurement to perform, no observation to make, no experience to have. And if time without change is completely undetectable, Leibniz argued, then it is not the kind of thing physics should be committed to. He proposed instead that time is nothing more than the ordering of events, the structure of before and after that emerges from the relationships between things that happen. Remove the events, and you remove the time. There is no river flowing through an empty landscape. There is only the landscape, the events, and the patterns of succession among them. This is called relational time, and Newton hated it. The two men argued through intermediaries, and neither convinced the other. The debate was never settled in their lifetimes. It is, in a very real sense, still not settled today. When physicists argue about whether time is fundamental or emergent, they are replaying the Newton-Leibniz dispute with better mathematics and higher stakes. These two cracks, time's arrow being thermodynamic rather than fundamental, and time's existence being arguably relational rather than absolute, were present in classical physics all along. They did not cause a crisis, because the practical machinery worked so well, but they were there, waiting. And if you find this kind of deep dive into the nature of reality fascinating, it would genuinely mean a great deal to us if you'd like and subscribe. It helps more people find their way to these ideas. The true earthquake came in 1905, not from a tenured professor at a prestigious institution, but from a 26-year-old patent examiner in Bern, Switzerland, who had been unable to secure an academic position and spent his working days reviewing other people's inventions. Albert Einstein, in what he later described as the most productive period of his life, wrote 5 papers in a single year. Any one of them would have been enough to guarantee his place in history. Together, they transformed physics so fundamentally that the world they described and the world Newton had described share little more than the surface appearance of similarity. The paper that most directly demolished Newton's picture of time began with a question that seems almost mundane on the surface. What does it mean to say 2 events happen at the same time if those events occur at different locations? The question had a disturbing answer hidden inside it, and Einstein had the courage to look directly at that answer rather than flinch away. To see what he found, you need the context that had been building for decades before him. James Clerk Maxwell, in the 1860s and 1870s, had unified electricity and magnetism into a single elegant framework, and one of the consequences of that framework was a prediction. Electromagnetic waves travel through space at a specific speed, approximately 300,000 kilometers per. Second, this is the speed of light. Maxwell's equations gave the number directly, but there was a conceptual puzzle. In Newton's universe, speeds are always relative to something. A sound wave travels at about 340 meters per second relative to the air. A ball thrown forward on a moving train travels at the sum of its own speed and the train's speed relative to an observer on the ground. Every speed has a reference point. What was the reference point for light? The obvious answer at the time was that light, like sound, traveled through a medium. Sound waves need air. Perhaps light waves needed their own medium, called the luminiferous ether, a substance filling all of space. Light would then travel at its fixed speed relative to this ether, and observers moving through the ether would measure slightly different speeds depending on their direction and velocity. In 1887, Albert Michelson and Edward Morley designed an experiment to detect this difference. They built an extraordinarily sensitive instrument that split a beam of light into two perpendicular paths and recombined them, looking for the telltale interference that would reveal any difference in speed between the two directions. Earth orbits the Sun at about 30 kilometers per second, so it should be moving through the ether at a significant fraction of that speed depending on the season. The effect should have been detectable. The instrument was sensitive enough. They looked carefully. They found nothing. The speed of light was the same in every direction, regardless of the orientation of the apparatus, regardless of Earth's motion. They repeated the experiment under different conditions at different times of year. The result never changed. The ether, if it existed, had no detectable effect. Light behaved as if it simply had no reference medium at all, as if its speed was constant for everyone, regardless of their motion. Most physicists at the time found ways to preserve the ether concept anyway, adding auxiliary hypotheses that would explain away the null result. It was Einstein who took the experimental results seriously as a fundamental fact rather than a puzzle to be explained away. He did not try to save the ether. He asked what the universe would have to be like if the speed of light truly was the same for all observers, regardless of their own motion. What would that require of space and time? The answer was astonishing. It required that space and time not be independent. It required that what one observer measures as a purely spatial distance, another observer in motion could measure as a combination of space and time. It required that there be no universal now, no single present moment shared by all observers. Most radically, it required that time runs at different rates for observers moving relative to each other. This is time dilation, and it is not a philosophical position or an interpretive stance. It is a hard physical prediction, confirmed by experiment to extraordinary precision. Here is the core argument. Imagine a clock built from two parallel mirrors with a pulse of light bouncing back and forth between them. Each round trip of the light pulse is one tick. For an observer at rest relative to this clock, the light bounces straight up and down. The distance traveled per tick is simply the gap between the mirrors. But for an observer watching this clock move past them, the light pulse doesn't travel straight up and down. It travels a diagonal path, up and forward as the clock moves, then back down and forward again. This diagonal path is longer than the vertical path. Since the speed of light is the same for both observers, the moving clock's light pulse takes longer to complete each round trip. The moving clock ticks more slowly. There is no trick here, no sleight of hand. The moving clock genuinely, physically ticks more slowly as measured by the stationary observer. Not because of mechanical interference, not because of some perturbation in the clock's mechanism, but because time itself is running more slowly for the moving system. This is time dilation, and it follows directly and necessarily from the constancy of the speed of light. The effect is negligible at ordinary speeds. At the speeds of cars and aircraft, the time dilation is so small it would take billions of years to accumulate into a single second's discrepancy. But as velocity approaches the speed of light, the effect becomes enormous. At 90% of light speed, time passes about 2.3 times more slowly for the moving observer. At 99% of light speed, the factor is about 7. The closer you get to light speed, the more extreme the dilation becomes, growing toward infinity as velocity approaches the limit. This is not theoretical in the abstract sense. It has been measured directly, many times, in many ways. The most striking natural demonstration involves muons, subatomic particles created when cosmic rays slam into molecules in the upper atmosphere, about 15 kilometers above sea level. A muon is unstable. Left to itself, it decays in about 2.2 microseconds on average. Even traveling at close to the speed of light, simple arithmetic says a muon should travel only about 660 meters before half of them decay. 15 kilometers is 20 times that distance. By the time cosmic ray muons should reach sea level, they should almost all be gone. But they are not gone. Experiments detect enormous numbers of muons at sea level. Why? Because the muons are moving so fast, typically at 99% or more of the speed of light, that time dilation stretches their internal clock. From the muon's own perspective, only microseconds pass during the journey. But from our perspective, the muon's clock runs slowly enough that it survives the full trip through the atmosphere. The extended lifetime of cosmic ray muons is direct, unambiguous, quantitative confirmation of time dilation. It matches the relativistic prediction precisely. But time dilation, dramatic as it is only the beginning of what Einstein's special relativity does to the concept of time. The deeper blow is the relativity of simultaneity, the discovery that whether two events happen at the same time depends on who is asking. Consider two lightning bolts striking the opposite ends of a train that is moving along a track. An observer standing precisely in the middle of the track, equidistant from both strike points, sees both flashes at the same moment and concludes the bolts struck simultaneously. But an observer sitting in the exact middle of the moving train sees something different. The train is carrying that observer toward the front strike point and away from the rear one. Light from the front flash reaches the train's midpoint slightly before light from the rear flash does. The train observer concludes the front bolt struck first. Both observers are correct. Both are applying the laws of physics consistently. Both are equidistant from the respective strike points in their own reference frames. The disagreement is not a measurement error. It is not a failure of communication. It is a fundamental feature of reality. There is no observer-independent fact about whether the two bolts struck simultaneously. Simultaneity is relative. It depends on motion. This single fact, once absorbed, collapses the entire Newtonian picture. If simultaneity is relative, then there is no universal now. There is no single present moment that spans the universe and is shared by all observers. What counts as happening right now at a distant location depends on your state of motion. A person moving away from a distant galaxy at high speed has a very different set of events in their now than a person moving toward that galaxy. Both nows are equally valid. Neither is more real than the other. This leads many physicists and philosophers to what is called the block universe, the idea that past, present, and future are equally real and coexist in a four-dimensional structure, with no privileged moving now. In this picture, events don't become real by happening. They simply exist at their locations in space-time. What we experience as the passage of time, the movement of now from past toward future, is not a feature of the universe itself. It is a feature of consciousness, something we do, not something the cosmos does. The universe is a static block. We move through it like a reader's eyes moving across a page, creating the illusion of progression while the page itself stays still. The block universe is philosophically controversial and deeply counterintuitive. It implies that the future already exists, fully formed and waiting, and that our experience of things, as yet undecided, is an illusion of perspective. Many physicists accept it as the most natural reading of special relativity, others reject it vigorously. But nearly all agree on the underlying physics: simultaneity is relative, there is no universal now, and time is not what Newton said it was. In 1915, Einstein went further. His general theory of relativity, which extended the ideas of special relativity to include accelerated motion and gravity, revealed something even more radical. Gravity is not a force, it is geometry. Mass and energy curve the four-dimensional fabric of spacetime, and what we experience as gravitational attraction is the path that free-falling objects follow through that curved geometry, the straightest possible line through a warped surface. Planets don't orbit the sun because they're pulled. They follow the curvature of the spacetime that the sun's mass creates around itself. And here is what this means for time. Since time is part of spacetime, and since spacetime is curved by mass and energy, time itself curves. Clocks run at different rates depending on the gravitational field they're sitting in. A clock at the top of a tall building, slightly farther from Earth's center and experiencing slightly weaker gravity, runs faster than a clock at ground level. The difference is tiny, a few nanoseconds per day for heights accessible to ordinary buildings, but it is real, it is measurable, and it has been measured many times with great precision. One of the most important confirmations comes from a technology most people use daily without realizing its connection to fundamental physics. The Global Positioning System relies on a network of satellites carrying precise atomic clocks. Those satellites are orbiting about 20,000 kilometers above Earth's surface. Two relativistic effects act on their clocks simultaneously. Their orbital velocity causes special relativistic time dilation, making their clocks run slightly slower than ground-based clocks, an effect of about 7 microseconds per day. But their position high in Earth's gravitational field causes general relativistic time dilation in the opposite direction, making their clocks run faster than ground-based ones, an effect of about 45 microseconds per day. The net result is that satellite clocks run fast by about 38 microseconds per day relative to ground clocks. 38 microseconds sounds negligible, but GPS works by measuring the precise time it takes for a signal to travel from the satellite to your phone. Light travels about 11 kilometers in 38 microseconds. If satellite clocks were not corrected for relativistic effects, GPS position errors would accumulate at roughly 11 kilometers per day, rendering the system useless within hours. Every GPS device on Earth, every phone, every navigation system, every emergency locator, quietly applies Einstein's corrections to keep working. Relativity is not an exotic corner of physics relevant only to astronomers and particle accelerators. It is embedded in the infrastructure of everyday life. General relativity also predicts, an experiment has confirmed, objects so extreme that time behaves near them in ways that strain language. A black hole is a region of space-time where the curvature becomes so severe that nothing can escape, not light, not matter, not information of any kind. At the boundary of a black hole, the event horizon, time dilation becomes infinite. An observer watching from a safe distance would see someone falling toward the horizon slow to a crawl, their movements becoming ever more sluggish, their light ever more red-shifted, as they approach but never quite reach the boundary. From the distant observer's perspective, the infalling person takes literally infinite time to cross the horizon. But from the infalling person's own perspective, nothing special happens at the horizon. They cross it in finite time, feel no dramatic boundary, and continue inward. The discrepancy is not an illusion on either side. It is time, behaving differently in different places, as measured by different observers. Both experiences are real. Both are consistent with the physics. They simply occur in profoundly different regions of an extraordinarily warped spacetime. Inside the black hole, the geometry becomes so distorted that the concepts of space and time exchange roles. Outside, you can move freely in space, but cannot avoid moving forward in time. Inside, the movement toward the central singularity is not optional spatial motion you can choose to resist. It is temporal, it lies in your future the way tomorrow lies in your future right now, unavoidable regardless of which direction you point your rockets. The singularity is not a place, it is a when. There is one more achievement of general relativity worth dwelling on, because it revealed that space-time is not merely warped. It can move. In 1916, Einstein predicted that violent events in the cosmos, two massive stars spiraling into each other and merging, two black holes colliding, would send ripples outward through the fabric of space-time itself. These gravitational waves would travel at the speed of light, stretching and compressing distances as they passed, physically altering the geometry of space and the rate of time everywhere they reached. Einstein predicted these waves, and then, characteristically, doubted they could ever be detected. The stretching and compression they would produce was almost impossibly small. For even the most violent events in the observable universe, the effect reaching Earth would be smaller than the diameter of a single proton spread across a distance of 4 kilometers. It took nearly a century to build instruments sensitive enough to detect that effect. On September 14, 2015, 2 detectors in the United States, each consisting of 2 tunnels 4 kilometers long, at right angles to each other, with laser beams bouncing back and forth to detect any change in length, registered a signal lasting about 1/5 of a second. The signal matched, with breathtaking precision, the prediction of general relativity for 2 black holes about 30 times the mass of the Sun merging into one. In the fraction of a second that merger lasted, it released more energy than all the stars in the observable universe combined, entirely in the form of gravitational waves. What was detected was not a force, not a particle, not a field. It was the fabric of space-time itself flexing. The signal confirmed not only that gravitational waves exist, but that space-time is a dynamic, physical entity that can vibrate and carry energy. Time, as part of that entity, is not a static background. It oscillates, it ripples. The universe does not unfold against a fixed stage. The stage itself is in motion. All of this, the relativity of time, gravitational time dilation, the block universe, rippling space-time, represents a picture of time radically different from Newton's. But here is the crucial point, and it is not appreciated nearly often enough. Even with all of this progress, even after the complete overthrow of absolute time and the replacement of Newton's picture with Einstein's, physics still does not fully answer the question of what time fundamentally is. General relativity tells us how time behaves. It gives equations of extraordinary precision describing how space-time curves, how clocks run in different gravitational fields, how different observers relate their experiences of duration. The equations work. They match experiment to extraordinary degrees of precision. But they don't explain why there is a temporal dimension in the first place, why time seems to flow when the equations describe a static 4-dimensional structure, why the past feels gone and the future feels open when the block universe interpretation suggests all moments coexist equally. The equations are a map, an extraordinarily accurate and detailed map. But the map is not the territory, and the territory, the actual nature of time, remains mysterious. And then there is the second great framework of 20th century physics, and it does not agree with the first one. Not in its predictions in ordinary domains, Both quantum mechanics and general relativity make predictions in their respective realms that are confirmed with staggering accuracy. They disagree about something more fundamental. They disagree about what time is. Quantum mechanics is the theory that governs the behavior of matter and energy at the smallest scales. Atoms, electrons, photons, quarks, everything that makes up the physical world obeys quantum mechanics at the fundamental level. The theory was developed in a burst of revolutionary creativity in the 1920s by a remarkable collection of physicists: Heisenberg, Schrödinger, Bohr, Dirac, Born, Pauli, who were trying to explain phenomena that classical physics simply could not account for. The way atoms emit light only at specific frequencies. The way electrons can tunnel through barriers they classically shouldn't be able to cross. The way certain measurable quantities come in discrete chunks rather than varying continuously. The resulting theory is the most precisely tested in the history of science. Its predictions have been confirmed to accuracies better than 1 part in 10 billion. It underlies everything from the design of semiconductors to the operation of lasers to our understanding of chemical bonding. Without quantum mechanics, modern technology, computers, emery machines, solar cells would be impossible. The theory works, spectacularly and without exception, in every domain where it has been applied. But quantum mechanics has a very strange relationship with time, and that strangeness is the source of one of the deepest unresolved problems in all of physics. In quantum mechanics, most physical quantities are described by mathematical objects called operators, abstract entities that, when applied to the quantum state of a system, yield the possible values that quantity can take when measured. Position is an operator. Momentum is an operator. Energy is an operator. Spin is an operator. When you measure any of these quantities, the quantum system doesn't simply report a pre-existing value. Before measurement, the system exists in a superposition, a quantum state that contains multiple possible outcomes simultaneously, with specific probabilities attached to each. The act of measurement forces the system into one particular outcome, selected randomly according to those probabilities. Time is not an operator. This is one of the strangest and most underappreciated facts about quantum mechanics, and its implications are enormous. Time in the standard formulation of quantum mechanics is an external parameter. It is the label on the laboratory clock. It is the independent variable in the Schrödinger equation, the master equation that describes how quantum states evolve. The Schrödinger equation says, given the quantum state at time t, here is the state at time t plus some small interval. Time is the input. The quantum state is what evolves. Time itself is not something the theory describes or predicts or assigns probabilities to. It is the background against which the quantum drama unfolds. This is a profound asymmetry. Position is a quantum observable, uncertain, fuzzy, subject to superposition, fundamentally described by probability. Time is not. You can ask where a particle is and get a probabilistic answer reflecting genuine quantum indeterminacy. You cannot ask when something happens and get an equivalent quantum answer, because time has no when operator whose eigenvalues would represent possible measurement outcomes. You have to read the time off an external classical clock that is not part of the quantum system at all. Wolfgang Pauli recognized early on why this asymmetry must exist. If there were a time operator in quantum mechanics, it would need to be what physicists call conjugate to the energy operator, in the same relationship that position and momentum share, where the famous uncertainty principle applies. A time operator conjugate to energy would imply that energy could take any value from negative infinity to positive infinity. But physical systems must have a ground state, a lowest possible energy. Electrons and atoms must have a minimum energy. Otherwise, atoms would radiate energy endlessly and collapse instantaneously. If energy could be arbitrarily negative, there could be no stable matter. The entire material world would be impossible. A time operator is therefore mathematically inconsistent with a stable physical world, and quantum mechanics was built without one. Time in quantum mechanics is classical and external. It is the clock on the wall, not the particle in the box. It does not fluctuate. It does not have uncertainty. It does not exist in superposition. It is the smooth, continuous, deterministic backdrop against which all quantum uncertainty plays out. This is already in tension with general relativity, which says time is dynamic, curved by mass and energy, part of the physical system being described rather than an external frame imposed upon it. In general relativity, you cannot separate time from the physical content of the universe. They are intertwined, each shaping the other. In quantum mechanics, that separation is mandatory. Time must be external. It cannot be part of the system. These two requirements are contradictory. You cannot build a theory in which time is simultaneously a dynamic part of the physical system being described and a fixed external parameter providing the framework for description. The contradiction is not a technical problem awaiting a clever mathematical trick. It is a conceptual problem about the very nature of time, and it becomes catastrophic when you try to combine the two theories into a unified framework. Before arriving at that catastrophe, quantum mechanics itself has more to say about time, puzzles that exist even without invoking gravity. The most famous involves the measurement problem, which is really a problem about what happens at specific moments in time and whether those moments are fundamentally special. The Schrödinger equation describes the evolution of quantum states smoothly, deterministically, and reversibly. Feed it a quantum state at any moment, and it gives you the state at any other moment, forward or backward, with perfect precision. This evolution is time-symmetric. It works equally well in both directions. No moment is privileged over any other. No direction of time is preferred. The equation is a machine for computing states, and it does not care whether the machine is running forward or in reverse. But measurement, the process of actually obtaining a definite outcome from a quantum superposition, is different. Before you measure the spin of an electron, it may be in a quantum superposition of spin up and spin down, a fuzzy combination of both possibilities. After you measure it, you get a specific result, either spin up or spin down, with probabilities given by the quantum state. The superposition appears to have collapsed into a single, definite outcome. This collapse, if it is a real physical process, is irreversible. You cannot uncollapse a wave function. You cannot unmeasure a particle. The information about the pre-measurement superposition appears to be lost, and this irreversibility introduces a genuine arrow of time into quantum mechanics, a distinction between before the measurement position, possibilities, quantum fuzziness, and after it, definite outcome, history, classical reality. The moment of measurement is qualitatively different from all other moments. The difficulty is that nobody agrees on what measurement actually is, or whether collapse is a real physical process. This is the measurement problem, unresolved since the 1920s, and it has spawned a proliferation of interpretations of quantum mechanics, each one telling a radically different story about time. In the Copenhagen interpretation, the wave function collapses when a measurement occurs, but the theory does not explain what triggers a measurement or why collapse happens. The collapse is simply a rule. When you observe, this is what you do to the wave function. Time plays its standard external role, and the collapse introduces an irreversible before and after, but the mechanism is left deliberately unspecified. In the many worlds interpretation, there is no collapse at all. When a measurement occurs, the universe branches. In one branch, the electron is spin up. In another, it is spin down. Both outcomes occur, each in its own branch of reality. The Schrödinger equation applies universally and without exception to electrons, to measuring devices, to physicists, to everything. There is no moment where the smooth unitary evolution stops and something discontinuous happens. From this perspective, Time is perfectly symmetric at the fundamental level, and the arrow of time must be explained entirely by thermodynamics and initial conditions, as in classical physics. But the branching structure of an ever-proliferating tree of universes gives reality a peculiar kind of temporal texture, not a single past giving way to a single future, but a single past giving way to a vast and constantly multiplying plurality of futures, all equally real. In objective collapse theories, pioneered by Girardi, Rimini, and Weber in the 1980s, collapse is a genuine physical process, not triggered by observation, but happening spontaneously, randomly, with a very small probability at any given moment for any given particle. For individual particles, the collapse probability is so low that superpositions persist long enough to produce all the quantum behavior we observe. But for macroscopic objects made of billions of particles, at least one collapse occurs almost instantaneously, keeping large-scale objects in definite states. These theories introduce a real arrow of time through spontaneous, irreversible collapse events. Time flows because the wave function genuinely, physically, and irreversibly collapses. In pilot wave theory, associated with de Broglie and Bohm, particles always have definite positions and definite trajectories. They are guided by a quantum wave that evolves according to the Schrödinger equation. Measurement outcomes are not random at the fundamental level, they are determined by initial conditions we do not have access to. Time plays a clean, straightforward role as the parameter along which definite trajectories unfold. It is the closest of all the interpretations to Newton's picture of time as a smooth external parameter, but now with quantum waves guiding the motion. These interpretations are not merely philosophical flavors. They disagree about what time does at the most fundamental level, whether it has a preferred direction, whether specific moments are genuinely special, whether the future is real. And none of them has been experimentally distinguished from the others, because they all make identical predictions for any experiment we currently know how to perform. The question of which interpretation is correct is thus, at present, not a scientific question in the ordinary sense. It is a question about the metaphysics of time, about what time is, not just how it behaves, and physics has not resolved it. There is, however, a phenomenon that cuts across interpretation boundaries and provides a genuinely physical story about why the quantum world gives way to the classical world we experience: decoherence. Understanding decoherence is essential to understanding the relationship between quantum mechanics and our experience of time. A quantum system in isolation can maintain a superposition indefinitely. An electron in an isolated laboratory can be in a superposition of spin up and spin down for as long as it remains undisturbed. But in the real world, nothing is truly isolated. Every system interacts with its environment, air molecules collide with it, photons scatter off it, thermal radiation bathes it. Each of these interactions entangles the system with the environment. Quantum information about the superposition leaks out into the surrounding world. The superposition doesn't vanish, it becomes entangled with so many environmental degrees of freedom that it becomes, for all practical purposes, impossible to observe. The result is that the system appears classical. To an observer who can only access the system directly, not the vast entangled environment, the superposition has effectively collapsed. The system behaves as if it has a definite state. This process happens at speeds that are almost incomprehensibly fast for macroscopic objects. For something as small as a single large molecule interacting with air at room temperature, decoherence takes a fraction of a billionth of a second. For an object the size of a dust grain, it happens in a time so short that no physical process can occur on a shorter scale. By the time any observer could begin to probe for quantum behavior, it has already been irreversibly lost into the environment. Crucially, decoherence is irreversible in practice. The quantum information doesn't disappear, it spreads across trillions upon trillions of environmental particles, each one carrying away an infinitesimal fragment of the original quantum state. Recovering that information would require tracking and perfectly reversing the quantum states of every single environmental particle simultaneously. This is technically not forbidden by the laws of physics, but it is practically impossible to a degree that dwarfs any conceivable limitation of technology. The information is gone for all purposes that matter. This creates an arrow of time rooted in quantum mechanics itself. The moment before decoherence, the system is in a quantum superposition, fundamentally indeterminate, with the future genuinely open. The moment after, the system has an effective classical state, and the quantum indeterminacy has been dissolved into an inaccessible environment. Before and after are qualitatively different. The transition is irreversible. Time, through decoherence, acquires a direction. And decoherence provides something classical thermodynamics alone could not, a mechanism by which the quantum world produces the classical world. Why does the chair in the corner of the room have a definite position rather than existing in a quantum superposition spread across multiple locations? Not because chairs are made of different stuff than electrons. Because the chair is interacting with trillions of air molecules per second, each collision entangling the chair's position with the environment, decohering any superposition before it could develop. The chair's position is being measured by the universe thousands of billions of times per second, and the universe's quantum record of those measurements is so vast and so entangled that it constitutes, in practice, a classical fact about where the chair is. Everything definite in our experience, every object in a specific location, every event that has unmistakably occurred, every feature of the world that has the character of fixed classical reality rather than quantum possibility, all of this is the residue of decoherence. The universe is constantly measuring itself, constantly turning quantum potentiality into classical history. And that process has a direction. It moves from coherent quantum states toward decoherent classical states, and never in reverse. It is the mechanism by which time flows. Now comes the precipice. Now comes the place where the two great frameworks of 20th century physics, relativity and quantum mechanics, are forced to confront each other, and where the problem of time becomes not merely puzzling, but mathematically acute and philosophically vertiginous. General relativity is a spectacularly successful theory of the very large. Planets, stars, galaxies, the structure of the cosmos itself. Quantum mechanics is an equally spectacular theory of the very small. Atoms, particles, the fundamental constituents of matter. In almost all practical situations, they operate in different regimes and can be used independently without conflict. A quantum chemist calculating the electronic structure of a molecule doesn't need to worry about spacetime curvature. A cosmologist modeling the large-scale structure of the universe doesn't need to worry about quantum uncertainty in individual particle positions. The theories occupy different scales, and at their respective scales, each works perfectly. But there are situations where both are unavoidably relevant simultaneously. The interior of a black hole, where matter is compressed to fantastically small volumes and quantum effects become important precisely where gravitational effects are also extreme. The very early universe, in the first instance after the Big Bang, when the entire observable cosmos was compressed into a region where quantum mechanics cannot be ignored, but gravity was the dominant force. The singularity that general relativity predicts at the centers of black holes and at the origin of the universe, a point where density becomes infinite and all known physics breaks down. At these places, you need both theories together, and when you try to put them together, the result is mathematical catastrophe. Quantum field theory, the synthesis of quantum mechanics with special relativity, is the framework that underlies the standard model of particle physics, the theory describing all known fundamental particles and all forces except gravity. It works by quantizing fields. Instead of particles as classical objects, you have fields pervading all of space, and particles are excitations of those fields. Photons are excitations of the electromagnetic field. Electrons are excitations of the electron field, and so on. The mathematical machinery of quantum field theory is elaborate and often forbidding, but it produces predictions of astonishing accuracy. When physicists try to apply the same approach to gravity, when they try to quantize the gravitational field, treating the geometry of spacetime as a quantum field that can be in superposition and described probabilistically, the mathematics falls apart almost immediately. The calculations produce infinities everywhere, and unlike in quantum electrodynamics where the infinities can be tamed by a procedure called renormalization, the infinities in quantum gravity resist every known technique for elimination. The theory is non-renormalizable, meaning it generates meaningless predictions rather than computable numbers. This breakdown is not just a technical failure. It is a sign that something fundamental is wrong with the conceptual framework. The deepest expression of that wrongness is the problem of time. When physicists attempt to quantize general relativity using the most natural approach, a procedure called canonical quantization, they write down the quantum analog of the energy constraint that gravity imposes. The result is an equation known as the Wheeler-DeWitt equation, named for John Archibald Wheeler, who formulated the conceptual problem, and Bryce DeWitt, who wrote down the mathematics in the 1960s. The Wheeler-DeWitt equation is supposed to describe the quantum state of the universe, its wave function, which encodes the probabilities for all possible configurations of space-time geometry and matter fields. It is the deepest equation we have for quantum gravity, at least in this formulation, and it is deeply unsettling. The equation contains no time variable. There is no term representing change, no derivative with respect to time, no parameter that evolves. The equation is not a statement about how the universe's wave function changes from one moment to the next. It is a constraint, a condition that the wave function must satisfy. The wave function of the universe does not evolve, it simply is. Static, frozen, eternal. This is called the problem of time in quantum gravity, and it is not a peripheral technical issue. It is the central conceptual crisis of the attempt to unify our two greatest physical theories. The most fundamental equation we can write for the entire universe has no time in it, and yet the universe is manifestly not static. Stars form and die. Galaxies collide. Civilizations rise and fall. Children are born. People age. Everything changes. How can a timeless equation describe a universe overflowing with change? The absence of time from the Wheeler-DeWitt equation is not an accident or an error. It follows directly from a profound feature of general relativity called diffeomorphism invariance. In general relativity, the physics does not depend on how you label your coordinates. You can relabel your time axis however you like, stretch it, compress it, mix it with spatial coordinates, and the physical content of the theory is unchanged. This is a fundamental symmetry of the theory, deeply connected to Einstein's insight that there is no preferred reference frame. When this symmetry is translated into the quantum theory, it forces the Hamiltonian, the operator that would normally generate time evolution, to be zero. There is no generator of time evolution, because in a fully general relativistic theory, there is no preferred time to evolve with respect to. The result is an equation with no time. How do physicists respond to this? The range of responses is a fascinating map of the different views of what time fundamentally is. One response is to argue that time is emergent, that the Wheeler-DeWitt equation's timelessness is not a bug, but a feature, revealing that time is not a fundamental ingredient of reality, but a derived concept that appears when you examine the quantum state in the right way. In a timeless wave function, certain correlations exist between different parts of the universe. Some degrees of freedom can serve as clocks. They carry information about other degrees of freedom in a way that mimics temporal relationships. When you look at the universe from within, treating some physical process as a reference clock, you recover the appearance of time. The universe looks as though it is evolving, as though events are ordered in time, as though there is a past and a future. This is sometimes called the relational approach to time, and it is a direct descendant of the philosophical position Leibniz argued for against Newton. Time is not fundamental. It is the pattern of correlations within a timeless quantum state. It is what you see when you look at one part of the universe and use it to keep track of another part. There is no external clock. There is no flow. There is only the structure of quantum entanglement and correlation, from which the experience of temporal sequence emerges. Carlo Rovelli, one of the founders of loop quantum gravity, has pursued this idea with great depth and elegance. In his thermal time hypothesis, developed with Alain Connes, Rovelli proposes that the flow of time we experience arises from our statistical ignorance about the microscopic state of the universe. We are macroscopic beings with access only to coarse, grained information about the detailed quantum state around us. That ignorance is not merely a limitation of our instruments. It is, in a precise mathematical sense, what generates time. Given any statistical state of a quantum system, there is a natural flow, a one-parameter group of transformations that the mathematics uniquely singles out. This thermal time flow is what we experience as the passage of time. It is real, but it is not fundamental. It is a feature of our relationship to the universe, not a feature of the universe as seen from nowhere. Loop quantum gravity takes this further. In its canonical formulation, the Wheeler-DeWitt equation appears in full, and the challenge of extracting time from a timeless equation must be confronted directly. Loop quantum gravity also quantizes space itself, proposing that at the smallest scale, the Planck length, about 10 to the power of minus 35 meters, space is not smooth and continuous, but made of discrete quantum units. Area and volume come in minimum chunks, the way energy comes in quanta. The geometry of space is a quantum object, with its own superpositions and uncertainties. In this picture, the continuous smooth spacetime of general relativity is an approximation, valid at large scales the way the smooth surface of water is an approximation to the discrete molecular reality beneath. At the Planck scale, space itself is granular, and time, being part of spacetime, may also be discrete, a succession of quantum geometric states rather than a smooth continuous flow. String theory takes a different approach. In its best understood formulations, string theory is defined on a fixed background spacetime. Time is given in advance as an external parameter, closer to the quantum mechanical conception than the general relativistic one. The fundamental objects are not point particles, but tiny vibrating strings, and the different modes of vibration correspond to different particles. The mathematical framework is extraordinarily rich and has produced deep insights into the structure of quantum field theory, the properties of black holes, and the nature of dualities between seemingly different physical descriptions. But string theory's reliance on a fixed background spacetime is both a strength and a weakness. It sidesteps the problem of time by not trying to quantize time, but at the cost of not being able to describe the full dynamics of spacetime itself. The background must be put in by hand. How it was chosen, why it has the properties it has, how it relates to the dynamical spacetime of general relativity, these remain deep, unresolved questions. The most important insight string theory has generated about time comes from a remarkable discovery made in 1997 by Juan Maldacena. He showed that a gravitational theory in a certain type of curved spacetime, called anti-de Sitter space, is exactly equivalent to a quantum field theory without gravity living on the boundary of that spacetime. The boundary theory has one fewer spatial dimension than the interior. The three-dimensional interior with gravity is encoded holographically in a two-dimensional boundary without gravity. This AD/CFT correspondence, as it is called, has profound implications for the problem of time. The boundary theory is an ordinary quantum field theory with an ordinary external time parameter. Time as quantum mechanics understands it, smooth and classical and external. The interior gravitational theory has dynamic spacetime. time as general relativity understands it, curved and active and internal. The correspondence says these two descriptions are exactly equivalent. The dynamic interior time and the external boundary time are two faces of the same underlying physics. If this equivalence holds, then time in the gravitational sense, the temporal dimension that curves and stretches in response to matter, can be understood as emerging from the quantum dynamics of a theory that has no gravity, where time is a simple external parameter. Gravitational time is not fundamental. It arises from something deeper. Whether this lesson applies to our actual universe, which has a positive rather than negative cosmological constant and very different large-scale geometry, is not known. Our universe is not anti-de Sitter space, and no equivalent of the Maldacena correspondence has been proven for our actual cosmological setting. But most physicists believe the underlying principle is general. Time, in the gravitational sense, emerges from quantum entanglement. Causal set theory offers yet another perspective, one that gives time a foundational rather than emergent status, but redefines what time fundamentally is. Developed by Raphael Sorkin and collaborators, the approach proposes that the basic structure of the universe is not a smooth, continuous spacetime, but a discrete collection of events with causal relationships between them. The pattern of which events can influence which other events, who lies and whose causal past and future, encodes all the geometry of spacetime, including its temporal structure. At a coarse-grained level, this discrete causal structure gives rise to the smooth, continuous spacetime of general relativity, the way the discrete lattice of atoms gives rise to the smooth, continuous material we experience macroscopically. In causal set theory, time is fundamental, but it is not continuous, and it is not a river flowing through an independent background. It is the pattern of causal precedence among discrete events. Some events genuinely come before others, and this ordering is physical and objective, not dependent on an observer's reference frame. The future is genuinely open, because new events are added to the causal set as the universe grows. This is the process by which time passes, not the flowing of time through events, but the actual creation of new events, each one genuinely novel, not contained in any prior state. This gives causal set theory a picture of time closer to our experience than the block universe of standard relativity. The present is real and privileged. The past is fixed and done. The future genuinely does not yet exist. Becoming is not an illusion. It is the most fundamental process in the universe. Roger Penrose has proposed something still more radical, that the mystery of time is inseparable from the mystery of quantum measurement. In standard quantum mechanics, the Schrödinger equation evolves states smoothly and reversibly, without any preferred direction of time. But measurement, or more precisely, what Penrose calls objective reduction, introduces irreversibility. And Penrose suspects that gravity is involved. His proposal is that quantum superpositions involve not just different quantum states, but different space-time geometries. Since any distribution of mass curves spacetime in a specific way, a superposition of two different mass distributions is also a superposition of two different spacetime. Geometries. General relativity, however, does not admit superpositions of geometries in any natural sense. The geometry of spacetime is supposed to be a definite classical field. When a superposition involves spacetime geometries that are sufficiently different, Penrose argues, the superposition becomes gravitationally unstable and collapses spontaneously into one or the other option. The timescale for this collapse depends on the gravitational energy difference between the superposed geometries. For small quantum systems, this timescale is astronomical, far longer than the age of the universe, which is why small quantum systems maintain coherent superpositions indefinitely in the absence of environmental disturbance. For large macroscopic objects, the timescale is vanishingly short, which is why macroscopic objects are always in definite classical states rather than quantum superpositions. If Penrose is right, the irreversibility of time, the arrow that makes the past fixed and the future open, is a gravitational phenomenon at its root. Events happen, definiteness emerges from quantum possibility, because of a deep interaction between quantum mechanics and the geometry of spacetime. The experience of time flowing is not merely thermodynamic or emergent from initial conditions. It is a fundamental feature of how the quantum and gravitational aspects of reality interact, an ongoing process of objective physical collapse that converts quantum potential into classical actuality, one irreversible event at a time. No one of these approaches has won the argument. Loop quantum gravity has produced rich mathematics and suggestive results about the structure of quantum spacetime, but has not yet made testable predictions distinguishable from general relativity in any experiment that can currently be performed. String theory and ADS-CFT have illuminated deep connections between gravity and quantum information, but have not produced a complete theory of quantum gravity for our actual universe. Causal set theory has a compelling conceptual framework, but faces serious challenges in recovering general relativity at large scales. Penrose's objective reduction is a physical hypothesis about the mechanism of wave function collapse, but experiments to test it have so far been technically out of reach, though increasingly ambitious efforts are being made. The disagreement is not a failure of physics, it is the frontier. And it is particularly striking that all these different approaches, using completely different mathematical frameworks, operating with completely different conceptual assumptions, reaching completely different conclusions about whether time is fundamental or emergent, discrete or continuous, real or perspectival, converge on a single deep consensus. Something about our current understanding of time is fundamentally incomplete. Consider what we know for certain. We know that Newton's absolute universal time is wrong. The universe does not have a single clock ticking the same for everyone. We know that time is dynamic, shaped by gravity, running at different rates for different observers, woven inseparably into the fabric of spacetime. We know that the laws of physics are overwhelmingly time-symmetric, and that the arrow of time we experience arises from the extraordinary improbability of the universe's initial state. We know that decoherence is the mechanism by which quantum indeterminacy gives way to classical definiteness, providing a microscopic basis for the experienced flow of time. We know that when general relativity and quantum mechanics are pushed to their common frontier, the concept of time either disappears entirely or transforms into something radically different from the concept in either parent theory. What we do not know is what time fundamentally is. We do not know whether it is a primary constituent of reality or a derived concept that emerges from something more basic. We do not know whether it is continuous or discrete at the smallest scales. We do not know whether the block universe is the correct picture, with all moments coexisting equally in a static four-dimensional structure, or whether time is genuinely flowing and becoming is genuinely real. We do not know whether the experienced arrow of time is entirely a thermodynamic and statistical affair, or whether it has a deeper quantum gravitational foundation. We do not know whether there was time before the universe, whether the Big Bang was an event in a pre-existing temporal framework, or whether time began with it, or whether the question even makes sense. These are not minor gaps. They sit at the center of our picture of reality, and they resist every tool we currently have. There is something profound in the nature of this particular ignorance. Of all the concepts in physics, time is the most intimate. Space surrounds us. Mass and energy describe the stuff we are made of. Charge and spin characterize particles we will never directly touch. But time is different. We live in it. We are made of it. In a sense, our bodies are processes, metabolic and neural and experiential, that unfold through time. Our memories are made of the past. Our intentions reach toward the future. Remove time and the very concept of a self, of a life, of experience itself, collapses. And yet this concept that is most intimate to us, most woven into the fabric of what it means to be a conscious being in the world, This is the concept that our deepest physics cannot adequately characterize. We can build clocks of breathtaking precision. We can synchronize them across continents using satellites. We can measure the rate at which time passes near a massive object, detect the ripples that spacetime itself makes when black holes collide, confirm that a particle flying through a detector lives longer than it should because its internal clock is running slow. Our practical command of time is extraordinary. But command is not understanding. You can drive a car without understanding internal combustion. You can use a clock without understanding time. The two are different enterprises, and for time, they remain more separated than for almost any other concept in science. There may be a lesson in how previous scientific revolutions resolved similar gaps. When physicists could not understand why hot objects glow the colors they do, why a heated piece of metal shifts from red to orange to white as its temperature rises, the correct answer required abandoning the assumption that energy could take any continuous value and replacing it with the. Radical idea that energy comes in discrete quantum chunks. The entire framework of classical physics had to be relinquished to make progress. When physicists could not understand what absolute rest meant for electromagnetic waves, the correct answer required abandoning the assumption of an absolute temporal framework and replacing it with the strange and counterintuitive world of relativity. The framework, not just the equations within it, had to change. The problem of time may require something similar. Not a new calculation within existing frameworks, but a new framework entirely. One in which the concepts of space, time, matter, information, and causality are understood at a deeper level. One in which the current contradiction between general relativity and quantum mechanics is resolved not by forcing one theory's concept of time onto the other, but by discovering a more fundamental concept from which both are derived as approximations. What would such a framework look like? Nobody knows. The honest answer is that we cannot fully anticipate it, because genuine conceptual revolutions are by definition not visible in advance, from within the conceptual framework being superseded. Newton's physics did not contain the seeds of special relativity in a form that made it predictable. The structure of classical physics did not make quantum mechanics an obvious next step. The next revolution in understanding time will likely be similarly unforeseeable from where we stand now. But we can glimpse, perhaps, some of the shapes it might take. If time is emergent, then the fundamental theory will be in some sense timeless at its deepest level, a description of quantum relationships and correlations from which temporal order arises statistically or structurally, without being built in from the start. The experience of time flowing would be revealed as something like the experience of heat, real at the macroscopic level, an extremely good description of something genuine, but not a fundamental feature of the microscopic reality. The block universe would be replaced by something even stranger, a timeless quantum state from which block universes emerge as approximate descriptions valid at scales far above the Planck length. If time is fundamental, then the deepest theory will have genuine temporal becoming built into its foundations. The future will be genuinely open at the level of the basic ontology, not merely at the level of our ignorance of initial conditions. Discrete events will come into being, one after another, in a process that is itself the most fundamental physical process. The causal set approach gestures in this direction, as does Penrose's objective reduction, though neither is yet a complete theory. If something else is fundamental, if the deepest level of reality is better described by quantum information, by the structure of entanglement, by the patterns of correlation in a vast Hilbert space, then both space and time may be emergent from something that does not look like space or time at all. The holographic principle suggests this is possible. ADS/CFT shows a concrete example. Whether the principle extends to our actual universe and what it would imply for the experience of time are among the deepest open questions in physics. The stakes of this question are not merely academic. Understanding what time fundamentally is would likely transform our understanding of the Big Bang, whether it was a genuine beginning in time or a transition from some prior state. Whether the concept of time extends through it or terminates at it or transforms radically in its vicinity. It would illuminate the interior of black holes, where our current theories predict that time behaves in ways that we cannot yet fully describe. It would potentially reveal whether the expansion of the universe will continue forever, or whether space-time has a finite future as well as a past. It would illuminate the deepest question of all. Why is there something rather than nothing? Why does the universe exist and undergo change rather than simply not existing? Why is there a story at all? These questions may sound philosophical rather than physical. In a sense, they are both. The boundary between deep physics and deep philosophy has never been sharp, and the problem of time sits precisely at that boundary. Physicists who work on it routinely engage with arguments from philosophy of time. Philosophers who think carefully about time must engage with the physics. The two enterprises need each other at this frontier, and the most productive workers in this space tend to take both seriously. What is remarkable, and what should perhaps inspire awe rather than frustration, is that after all the centuries of effort, after Newton and Leibniz, Einstein and Bohr, Schrödinger and Heisenberg, Wheeler and DeWitt, Penrose and Hawking and Rovelli, and 100 others of comparable brilliance, the question remains open, not because they failed, because the question is so deep. Because the answer, when it comes, will not be a minor adjustment to existing knowledge, but a reconceptualization of the most basic framework in which physical knowledge is organized. Measuring time is one of the oldest human activities, practiced in every culture across all of recorded history. Understanding time at the deepest level is among the newest and most unresolved problems of the most advanced science our civilization has produced. The gap between those two facts, between the act of measuring and the achievement of understanding, is a measure of just how strange reality is. The clocks tick, the satellites orbit, the gravitational waves ripple outward across billions of light years. The muons fall through the atmosphere, living longer than they should. All of it is real, all of it confirmed, all of it woven together by the mathematical fabric of our best theories. And underneath it all, waiting, stubbornly irreducible, resistant to every analytical tool we have brought to bear on it, is the question that started this journey. What is time? Not how do we measure it. We do that magnificently. Not how does it behave. We have mapped that in extraordinary and precise detail. But what is it? What is this thing that the clocks are counting, that the equations are describing, that consciousness is embedded in, that the universe appears to be made of in a way more fundamental than matter or energy or force? That question is still open. The search for its answer is the most important scientific project of the coming century. And the answer, when it finally comes, whether it tells us that time is the bedrock of reality or a beautiful illusion or something stranger and more wonderful than either, will not merely solve a puzzle in theoretical physics. It will tell us something final and irreducible about what it means for anything to exist at all. The clock ticks. The question waits. The answer is still out there. There is a dimension of this story that rarely gets told in popular accounts, the human dimension, the texture of what it actually feels like to work at this frontier. The physicists who spend their careers grappling with the problem of time are not working on puzzles with known solutions that just need clever manipulation to extract. They are working in the genuine dark, in a space where the mathematical tools themselves may be inadequate to the task, where the very language used to formulate the problem may be part of the problem. The concepts of before and after, of now and then, of cause and effect, these are embedded so deeply in language and thought that it is nearly impossible to ask a question about time without smuggling time into the asking. Consider what John Archibald Wheeler, one of the great physicists of the 20th century, and the man who first clearly articulated the problem that bears his name alongside DeWitt's, said about his own experience at this frontier. Wheeler spent decades thinking about the foundations of quantum mechanics and gravity. He coined the term black hole. He contributed to nuclear physics, to the theory of general relativity, to the conceptual foundations of quantum mechanics. And he returned, again and again, to the question of time, convinced that its resolution would require the most radical reconceptualization in the history of science. He spoke of physics as a kind of archaeology, digging through layers of successful but incomplete theory towards something more fundamental, and he suspected that at the deepest level, time would dissolve into something else entirely, something like pure information, or pure relationship, or pure. Logic. Wheeler's instinct that information is fundamental to the nature of time is shared by many contemporary researchers. In quantum mechanics, the act of measurement is fundamentally about information, about the transfer of information from a quantum system to a measuring apparatus, and eventually to a record that can be accessed. Decoherence is fundamentally about information spreading from a system into its environment. The arrow of time is fundamentally about the growth of correlations, the spread of information from concentrated local sources into diffuse global patterns that cannot be reversed. If time is deeply connected to information, then the theory that finally explains time may look less like a theory of physics in the traditional sense, and more like a theory of information, of how information can be stored, transmitted, correlated, and processed in a universe governed by quantum mechanics and constrained by the speed of light and the structure of spacetime. Some researchers working under the banner of quantum information theory believe that the concepts developed in that field, entanglement, entropy, quantum error correction, tensor networks, may be the natural language for expressing the deepest truths about spacetime and time. One startling result from this direction involves the relationship between entanglement and spacetime geometry. Physicists working with the ADS-CFT correspondence have found evidence that the geometric structure of the interior spacetime, including its temporal dimension, is encoded in the pattern of entanglement in the boundary quantum theory. More entanglement between distant parts of the boundary corresponds to more strongly connected interior geometry. Less entanglement corresponds to more disconnected geometry. The spatial and temporal structure of the gravitational interior appears to be built from the quantum information relationships of the boundary. This is perhaps the most concrete suggestion we have for how time might emerge from something more fundamental, not from a flowing river of absolute duration, not from the geometry of a pre-existing manifold, but from the pattern of quantum correlations between parts of a physical system, correlations that, at large scales, organize themselves into the structure we experience as space and time, with all the properties those concepts carry in our ordinary and scientific experience. If this is right, and it is a conditional of great weight, since we do not yet know whether the lesson of ADS/CFT generalizes to our actual universe, then the experience of time flowing is something like the experience of a very large number of entangled quantum degrees of freedom from the inside. You are not a consciousness moving through time. You are, in a sense, part of a vast pattern of quantum information whose internal structure has the property of producing, for sufficiently complex subsystems, the experience of sequential events, of memory and anticipation, of a persistent self moving from past toward future. The flow of time is the universe's quantum information doing what quantum information does, and the experience of that flow is what it is like to be one part of a large, entangled system in which entropy increases. That may sound reductive, as if it dissolves something precious and irreplaceable into mere computation. But it need not be heard that way. The fact that a rainbow can be explained in terms of the refraction of light through water droplets does not make it less beautiful or less real. The fact that music can be analyzed as periodic pressure waves in air does not make it less moving. If the experience of time flowing is the experience of quantum information organizing itself into the shape of a conscious being embedded in an entropic universe, if that is what time is at the deepest level, it does not follow that the experience is an illusion or that it matters less. It follows that reality is even richer than we supposed, that the universe contains in its most fundamental quantum structure the seeds of everything we value: experience, meaning, memory, anticipation, the sense of being alive in a world that changes. There is another thread worth following, one that connects the problem of time to questions about the nature of consciousness and experience. The philosopher of physics David Albert has argued that the particular version of the problem of time that modern physics presents us with, the combination of the timeless Wheeler-DeWitt equation, the thermodynamic arrow, and the quantum measurement problem, is not just a scientific puzzle, but a challenge to our entire way of being in the world. We experience time as flowing because we are remembering beings. The past feels fixed and done because our brains store records of it. The future feels open and undecided because our brains do not store records of it. But why do brains form records of the past and not of the future? Because entropy was lower in the past, which created the conditions for reliable causal chains that leave permanent imprints. Because decoherence converts quantum superpositions into definite classical states in a direction that points from low entropy past to high entropy future. Our entire subjective experience of time as flowing, as directional, as dividing reality into a remembered past and an anticipated future, all of it is rooted in thermodynamics and the special initial conditions of our universe. This is both humbling and astonishing. The most intimate feature of experience, the sense of being alive in a present moment moving through time, is contingent on the fact that the early universe happened to be in a state of very low entropy. If that initial condition had been different, there would be no arrow of time, no distinction between past and future at the macroscopic level, no possibility of beings who remember a past and anticipate a future. The experience of time is not written into the laws of physics. It is written into the accident of initial conditions. And those initial conditions themselves are not explained by any current theory. Why was the early universe in a state of such low entropy? Various proposals have been made. Roger Penrose has proposed that the low entropy of the Big Bang is connected to the specific geometry of the initial singularity, that a mathematical property called the Weyl curvature was constrained to be near zero at the beginning, creating a special highly symmetric and therefore low entropy. Initial state. Sean Carroll and Jennifer Chen have proposed that our observable universe is merely a pocket of order within a larger multiverse that is on average in a high entropy state, and that regions like ours form spontaneously and rarely from quantum fluctuations in an otherwise featureless equilibrium. Julian Barber has proposed that time itself is fundamentally an ordering of configurations, that the apparent direction of time arises simply from the structure of possible configurations of the universe and which ones can be neighbors of which others, without any underlying flow. None of these proposals is fully satisfactory. All of them push the question back, rather than resolving it. Why does the Weyl curvature start near zero? Why does the multiverse have the structure it has? Why are configurations ordered the way they are? The mystery retreats, but does not disappear. The initial conditions of the universe, and with them the arrow of time and the entire structure of our experience of temporal flow, remain among the deepest unsolved problems in physics and cosmology. There is one more perspective worth adding to this already rich and contested picture: the view from thermodynamics at the quantum frontier. Classical thermodynamics treats entropy as a property of macroscopic systems, defined in terms of the number of microscopic states consistent with the observed macroscopic behavior. Quantum thermodynamics, a more recent and rapidly developing field, extends these concepts to quantum systems where coherence and entanglement play essential roles. In quantum thermodynamics, entropy is generalized using the concept of quantum information entropy, and the second law takes on new subtleties when applied to systems that can maintain quantum coherence. One striking result from quantum thermodynamics concerns the relationship between entanglement and entropy. In a bipartite quantum system, a system divided into two parts, the entropy of each part is given by the entanglement between them. A highly entangled state has high entropy in each subsystem, even if the overall system is in a pure state with zero total entropy. This means that entanglement is literally a form of entropy, and since entropy is connected to the arrow of time, entanglement, one of the most distinctively quantum phenomena, is also connected to the arrow of time. This suggests that the arrow of time and the peculiarly quantum phenomenon of entanglement are not independent features of the universe. They are aspects of the same underlying reality. As quantum systems interact and become entangled with their environments, entanglement entropy grows, decoherence occurs, quantum superpositions give way to classical definiteness, and time acquires a direction. The quantum and the thermodynamic arrows of time are woven together. Both expressions of the growth of entanglement that occurs as a system interacts with a vastly larger environment. If the direction of time is rooted in the growth of entanglement, and if entanglement is fundamentally about quantum information, about correlations encoded in the quantum state, then the arrow of time is fundamentally an information-theoretic phenomenon. The universe moves from states of low entanglement to states of high entanglement. Low entanglement corresponds to the past. High entanglement corresponds to the future. The direction we call forward in time is the direction in which entanglement grows. And the experience of time flowing is the experience of being an entangled part of a universe in which entanglement is increasing. This is again a sketch rather than a complete theory. The mathematical details are active areas of research. The connection between quantum entanglement, the arrow of time, and the emergence of semi-classical spacetime is one of the most exciting frontiers in theoretical physics today. Researchers are using techniques from quantum information theory, tensor networks, quantum error-correcting codes, entanglement entropy, to probe the deep structure of spacetime and its temporal dimension. The language of physics is shifting. Equations are being written in the language of information and entanglement that would have been unrecognizable to physicists a generation ago. Something is changing. Whether it is a revolution in the making or an evolution toward a complete theory is not yet clear. What is clear is that the problem of time is not going away. It is getting harder, in a productive sense, more precisely formulated, more deeply understood in its difficulty, more connected to other deep open problems. The problem of time is connected to the problem of quantum gravity, which is connected to the problem of the nature of spacetime, which is connected to the problem of entanglement and information, which is connected to the problem of measurement and the emergence of classical reality, which is. Connected back to the problem of time. These are not separate puzzles. They are facets of a single underlying question, the question of what kind of thing the universe fundamentally is and how it produces, from whatever its deepest constituents are, the world of objects and events and experiences that we actually inhabit. Every clock ever built is in the end a machine for marking relationships, for correlating one process with another and producing a number that we agree to call the time. The atomic clock doesn't measure time in the sense of touching something called time and reporting its value. It counts oscillations of cesium atoms and uses the result as a standard against which other processes can be compared. time, from this perspective, is the name we give to a family of relationships among physical processes, relationships of before and after, of simultaneity and duration, of correlation and sequence. The name feels like it picks out something real, because those relationships are real. They are not inventions. The before and after of physical events are not imposed by human convention. They are features of the world. But what makes those relationships possible? What is the substrate in which they exist? What is the universe made of that allows events to stand in temporal relationships at all? That is the question that physics is still pursuing. And pursuing it has taken us from the confident serenity of Newton's absolute time, through the revolutionary strangeness of Einstein's relative time, through the quantum peculiarity of time as an external classical parameter, through the mathematical crisis of the Wheeler-DeWitt equation into a frontier where physicists debate whether time exists at all at the most fundamental level. The journey is not over. It may not be over for a very long time. But the journey itself, the sustained effort of human minds to understand the nature of the thing they are most immersed in, is one of the most remarkable stories in the history of knowledge. It is the story of a species clever enough to build clocks of extraordinary precision, wise enough to ask what the clocks are measuring, and humble enough to admit that after centuries of magnificent effort, they are not sure they know the answer. The clock ticks. The question waits. Somewhere, in mathematics not yet written and concepts not yet formed, the answer is waiting too.